Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very pleased to have Richard Cartwright with us today. Hey, Richard.
Hey, how's it going?
I am doing really well on this August 4th, 2021 in Phoenix, Arizona. We are a good toasty 43 degrees today or so.
Wow.
Yep, so it's Phoenix.
That's crazy.
Valley of the
It's pretty warm here too in Brentwood.
okay.
Which is in the Bay Area, but not quite next to the water, but close by.
Yeah, so you get a little bit more of the California Central Valley kind of weather.
Yeah, we do.
That's mediated by the ocean.
Yeah.
And where are you at? What's your institutional affiliation these days?
I'm at the SETI Institute, which is a nonprofit organization that has a lot of scientists working on different things at the Institute, planetary science primarily, although they dabble in other areas of astronomy as well. And there is still a large contingent of people doing the SETI, traditional SETI stuff. I'm on the other side of things, looking at solar system objects.
And speaking of, there's a lovely one there in your background.
Yeah. Yeah, this is the Uranian moon Ariel. It's probably my favorite solar system object. I guess if I have to pick one, it's probably Ariel.
All right.
And we're going to talk a lot about it in this paper that we're going to dive into in a little bit. So I'll wait for that, but the audience can get a taste with this image behind me.
Very cool. Very cool. And so in general, a little bit more broadly, Richard, what do you like to do for research?
Yeah, I'm trained as a geologist, but really I'm a spectroscopist.
Yep.
That's really my main thing. I use ground-based and space-based telescopes to observe solar system objects, primarily icy moons. I guess exclusively icy moons is what I do. And I'm interested in the UV through the near infrared, looking at what these objects are made out of, what can that tell us about what might be happening in the interiors of these moons. So looking at the connection between geology and chemistry. Yep. And then also, these materials that we see on the surfaces of these satellites, what can that tell us about how the solar system formed, how the Uranian subnebula formed, for example, speaking of Uranus and its moons. And so there's lots of other questions that come from that. But the main tool for me is spectroscopy.
Very nice. Very nice. And so that's going to bring us to this really lovely article on some objects that we haven't visited very recently.
That's right.
The science case for spacecraft exploration of the Uranian satellites, candidate ocean worlds in an ice giant system. And Richard, take us away.
Sure. So as I highlighted or previewed, I've spent a lot of time observing icy moons with telescopes, and the Uranian moons have really been a big part of this. And it's through that research as a graduate student and afterwards that I got more interested in these moons and trying to figure out what do we need? What are the science questions that can be answered with another spacecraft mission? So it's something that myself and of course this long list of colleagues and other people in the community have been thinking about and working toward. And along with what I call the classical moons, the 5 big moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, Uranus has a bunch of other moons too, just like the other gas or the other large planets of our solar system. It has a series of ring moons and also irregular satellites which orbit much further out. And we don't know that much about the classical moons, and we certainly know even less about the ring moons and the irregular satellites of Uranus. And so I wanted to put together these different groups of moons into one paper to make the case for why we should go back to Uranus, specifically with an orbiter, and get more data and try and learn more about these 27 moons. So that's kind of a nice little overview there.
Cool.
And then the paper dives pretty quickly into talking about the 5 big moons and the case that the geology that we see on these moons, which I think is so we're going to bounce around a little bit here, is in figure 2.
That's fine. Let's go to figure 2. Let's take a look at figure 2. And there we go. Yep, 5 classicals. There we go.
Yeah. And so in this image, A, B, and C are Miranda, the innermost moon. D and E are Ariel, the second moon. And then F is Umbriel, G is Titania, and H is Oberon.
Yep.
And Voyager 2, when it made its flyby of the Uranian system, got the closest to Miranda. And Miranda certainly did not disappoint in terms of having a really fascinating surface. It's dominated by these large polygonal regions called the coronae, which we're highlighting in some of these images in A through C. Yep. And then it got not that close, but fairly close to aerial. So now we're at a kilometer a pixel at this point, and we start to see these medial grooves, which are reminiscent of fissure-style volcanism on Earth. Not really sure what they are, but that's kind of what they remind us of. Right. Some other features which are hint at possible cryovolcanic activity, like partially infilled craters, like the one shown in E. Yeah. And then the 3 outer moons, unfortunately, we didn't get that close at all with Voyager. And the spatial resolution is anywhere between 3 to 6 kilometers per pixel. And so these image mosaics you see in F through H is about as good as it gets.
Yep.
So that's a little bit of background on the flyby of those moons. And so putting all the geologic evidence into context, and then some stuff with the telescopes as well, looking at the composition of these moons using spectroscopy, which I'll get into in a little bit. These moons are classified as candidate ocean worlds. And so an ocean world is a icy object that has an outer shell made out of water ice primarily, and then a subsurface liquid layer beneath it. Liquid being, either pure water with some contaminants in it, or maybe more of a slush, whatever. Right. An extremely malleable or liquid layer underneath the solid icy shell. And the measurements made by Voyager 2 are certainly insufficient to determine whether these moons are ocean worlds. And some important examples would include things like Enceladus, where we know there's plume activity jetting material out into space. Europa and the other icy Galilean moons have subsurface water oceans, and we know that from measurements of induced magnetic fields in their interiors and other sets of measurements as well. And so the 5 largest uranium moons could also be ocean worlds. And this is important to study in terms of NASA's priorities, because ocean worlds seem to display a spectrum of activity. So Ceres in the main belt is considered an ocean world, but is relatively, it's a primitive object, primordial object, I suppose, and has had some activity, but not that much. And then on the other end of the spectrum, you've got objects like Enceladus, which are clearly highly active. And the Uranian moons probably fall somewhere on that spectrum, but it's not clear where. And getting a full picture of what ocean worlds are requires making more measurements of objects like the Uranian moons to get a sense for the full picture of what ocean worlds are. So that's kind of some more of the motivation for why this is important to NASA's goals. Nice. And other than the Voyager 2 flyby, which was extremely brief, less than 24 hours, 35 years ago, using technology designed in the 1970s, that's all we have. And so we really need to send another spacecraft mission there to study these 5 large moons, and then the other 21 smaller moons too, 22 smaller moons as well. And so, and so this is the main thrust of this paper. And so that's a little bit about the geology. Now, unfortunately, Voyager 2 was not equipped with a near-infrared mapping spectrometer. So what we know about the composition of these moons comes from ground-based telescopes. And so we see some of this in figure 4, I believe, and 5, I guess. Right, and I might bounce between these two. Okay. So these are some ground-based spectra of aerial and titania collected with Spectraph on NASA's infrared telescope facility on Mauna Kea in Hawaii. Okay. And this is near infrared spectra, so about 0.7 to 2.5-ish microns, kind of classic JH and K bands. And these objects are rich in water ice. A fair amount of dark material, which dampens those water ice bands. They're actually relatively weak compared to icy satellites elsewhere. And some spectrally red material, especially on the outer moons, like Titania, which I have in that box there, trying to show that there's some slope. If we had visible wavelength coverage, that slope would be larger. And then also there's CO2 bands, which are pretty dead on for pure CO2 ice measured in the lab, which we see in particular, on aerial, those 3 bands there. which hang off the base of the 2-micron water ice band.
Yeah.
And so these features are really fascinating, the CO2 in particular, because we don't know where the CO2 comes from. And it could.
What is the vertical gray?
Those are caloric bands. So where Earth's atmosphere is more of a problem.
Okay. Yeah. Okay. Yep.
Yeah. Signal noise starts to drop off a little bit.
Mhm.
And so the CO2 is, we think, the preferred hypothesis is that the CO2 is generated by charged particles interacting with materials on the surfaces of these moons.
Okay.
And so making CO2 radiolytically, which is really easy to do actually in the lab. If you have water ice, you mix it with some carbon stuff, you can make CO2.
Okay.
But alternatively, the CO2 could be sourced from the interiors of these moons. And if that was the case, it might be indicative of recent geologic activity, because the CO2 shouldn't be there, we don't think, over geologic timescales, because it's thermodynamically stable. And so it's probably hasn't been there since the beginning of the solar system. It's probably more recent. And so it needs some sort of process either to be actively generating it or to replenish it from the interior.
Okay.
And then you've got all this evidence for tectonics and possible cryovolcanism on these moons that we were just looking at, and then the figure behind me. And so maybe the CO2 has seeped up from their interiors.
Mm-hmm.
And we can explore that, and we have explored that using ground-based telescopes and space-based telescopes, and in the near future with JWST as well. But these data are not spatially resolved, and that's the key. We can't tie the composition to specific geologic regions or units. And so we can't really say for sure where the CO2 came from. We can only characterize it in a spectral capacity.
Global way, right?
Yeah. And then if we go to the next figure, whichever one we're on, 6. This is looking at another tantalizing spectral feature in the plot on the right there.
Okay.
And this is a 2.2 micron band, which is very popular in for solar system astronomers on icy bodies. There's a range of different constituents that can make a band in this wavelength region, notably ammonia. And ammonia is really key because it's a good antifreeze when mixed with water. It's not the only one, but it's a good one.
Yep.
And so it can really depress the freezing temperature of water. And so the take home here is you can retain liquid oceans in the interiors of icy moons if a lot of ammonia is present at much lower temperatures. And so these bodies could retain oceans possibly into the recent past or perhaps to present day. And things like ammonia can help make that happen. Now, other species also absorb in the 2.2 micron range.
Whoa. And
so ammonia is not the only candidate. Carbonates can also do it, but carbonates would also be a possible indicator of geologic activity, recent geologic activity. As we see this on Ceres, where there's those bright salt deposits in the base of craters on Ceres, or Occator crater in particular, which are rich in both carbonates and ammonia. And so I think either way, whatever's causing 2.2 band could be a hint for recent geologic activity. And then as your cursor is going over it, so let's go there. Looking at this map here of Ariel. So this is the image behind me, but stretched out into a Mercator map projection. And each of the blue data points represents where a spectrum was collected, the mid-observation points, where a 2.2 band was detected at a statistically meaningful level.
Okay.
All the black dots are other observations where we didn't detect a 2.2 band at a statistically meaningful level, which doesn't mean it's not there. It's just that we just didn't quite get it good enough to feel confident in the detection. Now, it's important to note, just in case people aren't aware, that these data are not spatially resolved. This Ariel is absolutely a point source. And so these data points average over an entire hemisphere. So we don't know for sure if the ammonia is, or the 2.2 band, I should say, is concentrated in those tectonic features that those blue dots overprint, but that's where the signal is the strongest, for whatever that's worth. And to tie the 2.2 band to specific geologic units, we need the spatially resolved data from a spacecraft in orbit around Uranus. And we got a hint of what this might look like when New Horizons made the flyby of Charon and Pluto.
Right.
And there's a 2.2 band all over the place on the surface of Charon, which has been attributed to ammonia and also chemically similar ammonium compounds.
Right.
And so Ariel and the other uranium moons could have a similar situation where this 2.2 band is associated with certain geologic units, whether it's fresh craters, tectonic features, whatever, and it's ammonia that's been exposed from the surface. So maybe a salt-rich deposit.
Okay.
And similar to CO2, I didn't say this at the beginning, similar to CO2, ammonia is not stable over geologic timescales on these moons. Charged particles should rapidly degrade it into other constituents. So if it's really there, it got there somewhat recently, which again hints at recent activity. So again, going toward the evidence that these moons are candidate ocean worlds, because it looks like they've had some stuff happening in the recent past, and it's tantalizing.
Indeed. Yes.
Yeah, so that's kind of the compositional story for these moons as well. The other link there that I didn't mention is with the spectrally red material, which was in that previous figure, which seems to be concentrated, right there on Titania. It seems to be concentrated mostly on the outer moons, Titania and Oberon. We think it's a regular satellite dust that's migrating inwards due to Poynting Robinson drag, primarily coating the outer moons.
Okay.
So the canonical example of this is Iapetus and Phoebe, where we know, the leading hemisphere of Iapetus is very dark, much darker than its trailing side. And we think that's from the accumulation of dust from retrograde irregular satellites as this dust migrates inward due to Poynting Robinson drag.
Yep.
And something similar could be happening at Uranus. The mass complicated because Uranus has a large obliquity, right? So it actually, it's not in my pay grade, but there's apparently a chaotic zone where these dust grains, which are migrating inwards from the irregular satellites, they might reach this point in the orbits as they get closer to Uranus, where they experience large oscillations and their inclinations and eccentricities change over very short time scales. And then the dust gets a little wild and can end up on all the moons, which is why the example is not as clean as the Iapetus and Phoebe example. But the take home of those models, and if anyone's interested, it's Tamayo et al. 2013. It's an excellent paper.
Shout out.
Is the take home though is most of the dust would still end up on Titania and Oberon. So it's still consistent with this spectrally red material. And this is really neat because it could mean that these moons are getting coated with primitive or material from really primitive objects. Yeah. And this goes to another point, another part of this paper that we're interested in is these other moons we don't know anything about. You've got, so I guess figure one is probably best for this. Because we just don't know anything about irregular satellites anywhere in the solar system, and Uranus less so than Jupiter or Saturn. You've got these 9 known irregular satellites, right? So I should orient the audience a little bit here. On the left is the 5 classical moons we've been talking about in orbit around Uranus, and then the ring moon system where the ring moons reside. And then on the right, all of that good stuff is right in the center of that image. And then you've got these 9 irregular satellites orbiting at much larger semi-major axes from Uranus. 8 are retrograde, which are the red orbits. And then there's 1 prograde irregular satellite, which is the blue orbit. And so the theory is that the dust from the 8 irregular satellites, because of Poynting Robinson drag, as dust grains are liberated from the surfaces of the irregular satellites, this dust will migrate toward Uranus.
Okay.
Yeah, and so this dust that's ending up on Titania, or hypothetically ending up on Titania and Oberon, could originate from these very primitive objects, which might have originated in the primordial Kuiper belt. And so by studying the irregular satellites, we can really start to get a better picture of what the early solar system looked like. So the classical moons are important because they tell us about ocean world activity and possibly recently active bodies, which may have been harbors for life at some points, or maybe still are, right? So there's that tantalizing angle. And then the irregular satellites tell us about what the early solar system was like, what materials were present, and what these bodies may have, the material they may have accreted. These might be leftover embryos that didn't make it into any of the larger, more evolved objects, might be the leftover bits, right?
Yeah.
And so with the irregular satellites, one of the great things that Cassini did that I think gets overlooked a little bit is inbound to orbital insertion at Saturn. It made a close flyby of Phoebe.
Mhm.
And that flyby has paid major dividends for science for a bunch of different topics.
Good.
And I would love if an orbiter inbound to Uranus was able to make a close flyby of an irregular satellite before getting to Uranus. That could tell us just a phenomenal amount of things about these likely captured objects. So unfortunately, I don't have much else to say about irregular satellites. Don't know that much.
Right.
So yeah, but speaking of small bodies, then we should probably hit the ring moons too. So going to figure, I think it's 3. We don't have, well, we do have images of 1, Puck, the largest ring moon, and that's as good as it gets right there at 4.5 kilometers per pixel. It's
Fuzzy.
probably, yeah, it's pretty fuzzy, and that image has certainly been reprocessed. That's about as good as it gets.
Right.
And we just don't know that much about these ring moons. And Uranus has a very interesting, and I'm certainly not an expert in this, but it has a very interesting ring moon system, and it's very densely packed. And it has, I think, 9 moons. I can't remember which. I think it's from Cordelia to Belinda, or maybe it's to Perdita, that are packed within something like a semi-major axis of 25,000 kilometers, which is a very small distance. Something like that. It's in the paper. The specifics are in the paper. You should trust the paper and not what I'm saying out loud.
Okay.
Yeah, and this is really weird. And the dynamics of this system are something that we don't understand. Like, how can you have so many moons so close together? Are they stable over long time periods? How long before they might collide with each other? At least some of them might collide with each other. And so it's a really interesting problem. And then, my personal favorite ring moon, I suppose, as a non-expert in ring moons, is MAB. And MAB is very weird. It's a very small object. It's the outermost one. It orbits within the mu ring, which it probably sustains. So material off the surface of MAB is probably going into orbit and forming the mu ring around it, which is this dusty and diffuse ring. Some of this material probably ends up on the leading hemisphere of Puck, the inner moon there. Yeah, yep. And it's possible that some of this ring material migrates outwards and actually makes it to Miranda.
Yep.
So there's some interesting dynamics here in terms of understanding the relationship between the ring moons and then the inner classical moon Miranda. Have they shared material? Did MAB originate as part of Miranda and it got broken off in some sort of impact? Did it originate as a ring moon? There's a lot of different scenarios here. And so the ring moons are absolutely fascinating. And that's about all I can say about them. That's probably the extent of it. And so you've got these 27 moons. We don't really know that much about them. We're still collecting data, we're still making observations, and we're still reinterpreting, reanalyzing Voyager 2 images even 35 years later. There's still new papers coming out all the time.
Yes.
They're looking at these. Yeah, but really, we need to send a spacecraft back and get a new suite of data. And in particular, I didn't mention this before, the key instruments include a magnetometer, because we can use that to search for induced magnetic fields in the interiors of these moons. And other communities would want a magnetometer for a bunch of other reasons related to the planet itself.
Sure.
Then there is, of course, you need a camera, you need a good one over visible wavelengths. That's always a good idea. Put a camera on a spacecraft mission. We would want this to look for evidence for recent activity, possible connections between for ongoing activity, and also connections between the interior and the surface of the moon, of these moons. So looking for cryovolcanic sorts of conduits, that sort of thing.
Right.
And then the other thing, it shouldn't be a surprise to hear this from a spectroscopist, is a near infrared mapping spectrometer, which Voyager 2 did not have. And we do not have spatially resolved spectra of these moons. And we can't tie the compositions of these satellites to different geologic units. And that figure right there, I think, is the one below that, is a great one to think about, in this context. So in this figure, what you're seeing on the left and center are simulations of what Titania and Ariel might look like as seen by LUVOIR, assuming a LUVOIR was going to happen.
Right.
And this is, for the audience members who might not know, this is a proposed telescope that would go into, I think it's the Earth Moon L2 Lagrange point, and it would have a perhaps an 8-meter or 15-meter primary mirror, which would be fantastic, right? And so this would easily represent the premier facility in the next several decades. And these simulations are what these moons might look like. And it should be apparent, even though we'll get some tremendous data from these sorts of telescope observations, it should be apparent that data from 35 years ago, from technology developed in the 1970s, is far better from a spatial resolution perspective.
Yes.
You know, you can't do geology, even with the telescopes that are coming online with facilities like LUVOIR. You have to send a spacecraft to Uranus to really get at the geology. And, you know, so LUVOIR is going to do some great things, or would, I should say, if it is chosen. And so will the ELTs, the extremely large telescopes, which are ground-based telescopes, which are also going to be phenomenal facilities, and those are happening. But that's really on the composition side, I think, where you're going to see a lot of new discoveries being made on these moons and elsewhere in the solar system. In terms of geology, we really need a spacecraft.
Cool.
Yeah, so I think that's the paper in a nutshell.
Very nice, very nice. Richard, I want to thank you so much for walking us through your very lovely article.
Great, thank you. Thanks for having me.
Sure. And you hinted at it a couple of times. So I'll just give you another chance here to give it a future look.
Oh, sure.
You know, missions take a while.
They do.
You have to make the science case for them, and they got to go through, you know, it's a decade-long thing. So within a decade, we can hope that, you know, maybe one will be funded or you know, a test mission or something like that.
Sure.
But sort of where do we go over the next, let's say, 5 years to better make the case that the resources spent going to the Uranian system is worth it?
So that's an excellent question. There is definitely a time criticality component to this mission, in that if you want to go to Uranus, let's say on a budget, then you want to use a Jupiter gravity assist to get there faster. You want to make a close flyby of Jupiter and slingshot out further out into the solar system, right? Classic technique we've used before.
Right.
That launch window is between 2030 and 2034. That's when you need to launch to make it. That is certainly doable. With a suite of different mission classes, we can certainly make that launch window. But the take home there is there does need to be action in the next 10 years to get a spacecraft there, unless you utilize other technologies that can get you there in a timely fashion. That doesn't involve a Jupiter gravity assist, because you're going to lose that window and you're going to lose it for a good period of time.
Yes.
And so then in terms of the decadal survey, yeah, we did put in a white paper that covers a lot of the same grounds, making the case for an orbiter at Uranus specifically to, you know, study the moons. And that's in, and, you know, hopefully the decadal survey makes a recommendation about Uranus, but that doesn't, you know, that's just the starting point, right? If they make a recommendation, NASA headquarters can do what they want with that, to an extent, and they've got other priorities, which isn't to say that Uranus isn't a priority, but that they have to balance that with the whole suite of different mission options they want to fly over the next 10 years. And so there are different mission classes that could work. Flagship, of course, that's the big one. Cassini style mission would be fantastic if it went to Uranus, but that might not be realistic or feasible given other priorities like Mars sample return. And so other mission types, including New Frontiers, which is what New Horizons was and what Juno is, you know, they're in that class, that cost class, that could work for a Uranus orbiter. And Discovery would be an intriguing option. That's the real low, well, you know, from NASA's standpoint, low budget. Inexpensive, quote, in air quotes, mission class, which could also possibly work for Uranus, although I don't know if you can do an orbiter at that price. That might have to be another flyby. That's not, I'm not clear on that. That's something that would need to be investigated to see if you could do an orbiter at a lower cost, at that sort of a low cost. But these are kind of the options that we have over the next 10 years. And it is something, you know, if NASA wants to prioritize the mission to Uranus, now is definitely the time to start to make waves and start to make it happen.
Cool. All right. Well, I'll keep my fingers crossed.
Me too.
Out of the decadals here in the next months or so.
Yeah.
These roll throughs, very good. Well, Richard, I hope one of my future videos is you talking about these spectroscopy. Wonderful things that have come out from an orbiter.
Sure.
Around the Uranian satellites. That'd be really good. So thank you once again. And thank you, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Thank you. Bye-bye.
Bye.